There's an object racing toward Jupiter right now that's doing something comets aren't supposed to do. It's pointing a massive jet directly at the Sun, and that jet has stayed locked in place for months. That's not how physics works. That's not how any of this is supposed to work. Comets have tails that stream away from the Sun like hair blown back in wind. They've done this for as long as we've watched them. Every single one. Until now. NASA's watching it. Harvard scientists are analysing it. Observatories across multiple continents have confirmed what they're seeing, and the explanation requires unusual conditions that challenge standard comet models. This isn't speculation. This isn't internet rumour. This is documented, peer-reviewed strangeness happening in real time, and it's accelerating toward a date that might give us answers. March 2026, when this object will pass through Jupiter's gravitational sphere. The object is called 3I Atlas. The I stands for interstellar. It came from outside our solar system, carrying with it behaviours that don't match anything in our catalogue of cosmic objects. And in less than 3 months, it's going to thread past Jupiter at a distance close enough that the planet's immense gravity could either tear it apart, reveal what's beneath its mysterious dust veil, or change its trajectory in ways we can't predict. Stay with me for the next several minutes. We're going to break down what 3I Atlas is actually doing out there in the cold between Mars and Jupiter. We're going to look at the observations that keep stacking up, each one more difficult to explain than the last. We're going to examine why its rotation pattern looks mechanical when it should look chaotic. We're going to discuss what NASA's Europa Clipper spacecraft saw when it caught a view of this thing that Earth-based telescopes couldn't access. And we're going to talk about what scientists expect when it reaches Jupiter in March, and what might happen if those expectations are wrong. But first, if you're as fascinated by interstellar mysteries as I am, hit that like button right now, and drop a comment telling me this. Do you think we're watching a comet behaving strangely, or something we don't have a name for yet? Because that's the question hanging over every observation, every data point, every conversation happening in the astronomical community right now. The data is real. The observations are confirmed. The interpretations, well, that's where things get complicated. Before we dive into what makes 3I Atlas so strange, we need to establish what normal looks like, because without that baseline, the anomalies won't mean much to you. And once you understand how comets are supposed to behave, what this object is doing will seem even more unusual and harder to explain. You know how comets work, right? At least you think you do. Most of us have this mental image, a dirty snowball racing through space, warming up as it approaches the sun, sprouting a tail that streams behind it like the trail of a jet. That image is mostly accurate, but the details matter here, because those details are what 3I Atlas is violating. Comets are ancient repositories of ice, dust, and frozen gases. They formed billions of years ago in the cold outer reaches of solar systems, where temperatures are so low that water, carbon dioxide, ammonia, and methane freeze solid. These objects are cosmic time capsules, preserving the chemical signatures of their birth environment. For most of their existence, they drift through the void, inert and frozen. Nothing happens. They're just ice and rock moving through darkness. But when a comet falls toward the inner solar system, everything changes. The sun's radiation begins to warm it. The ice doesn't melt in the way water melts on Earth, because there's no atmospheric pressure out there to create liquid. Instead, it sublimates. It goes directly from solid to gas, skipping the liquid phase entirely. Think of dry ice on a warm counter. That ghostly vapor curling off its surface. That's sublimation. That's what happens to a comet. As the ice sublimates, it carries dust particles with it, creating a hazy atmosphere around the nucleus called a coma. The gas and dust then get pushed away from the comet by two forces: the solar wind, a stream of charged particles flowing out from the sun, and radiation pressure, the physical push exerted by sunlight itself. Yes, light has pressure. It's incredibly weak, but in space, over time, it's enough to push microscopic particles away from their source. This creates the tail. Actually, it creates two tails, though we usually see them blended together. The dust tail is made of larger particles that curve gently along the comet's orbital path following the physics of momentum. The ion tail, made of charged gas molecules, points almost perfectly away from the sun because those charged particles respond powerfully to the solar wind. Both tails point away, always away. This is the rule. This is what we've observed for centuries across thousands of comets. The tails can be millions of kilometers long, stretching across the sky in spectacular displays. But their direction is never in doubt. A comet's tail points away from the sun the same way smoke points away from a fire. It's not random. It's physics. The sun pushes, the tail responds. Now, why does this matter for jets? because jets are localized bursts of sublimation, often triggered when the comet's rotation exposes a pocket of volatile ice to direct sunlight. Imagine a rotating ball with a weak spot in its shell. When that weak spot faces the sun, the ice beneath heats rapidly, gas bursts outward, and you get a jet. These jets can be powerful enough to affect the comet's rotation and trajectory. They're messy though, random, dependent on the comet's internal structure, which is usually irregular, full of cavities and fractures and pockets of different materials. Most comets have multiple jets firing from different locations as they spin. These jets turn on and off as the rotation brings different areas into sunlight. The pattern is complex, unpredictable, and changes as the comet approaches and then moves away from the sun. Perihelion, the closest point to the sun, is when activity peaks. That's when the surface is hottest, when sublimation is most violent, when everything goes chaotic. After perihelion, comets usually calm down. The heating decreases, the jets weaken, the tail shrinks. The object settles back into a quieter state as it moves toward the cold outer solar system again. This is the life cycle. This is the pattern we've documented across every comet mission, every observation campaign, every close-up study we've ever conducted. So when you hear that 3i Atlas has a tail pointing toward the sun, your brain should reject that immediately. When you hear that it's sustained this impossible tail for months, past perihelion, while heading outward, you should be confused. When you hear that it has a single dominant jet that wobbles with mechanical precision instead of multiple chaotic jets, you should start asking questions, because none of that fits the baseline. None of that is what comets do, and that's exactly why astronomers can't stop watching it, because 3i Atlas is rewriting the script, and nobody knows if we're looking at an extreme edge case of natural behavior or something else entirely. Let me describe what observers have been seeing over recent months, because the visual alone should tell you something's off. 3i Atlas has a tail, a long persistent tail made of dust and particles. But this tail doesn't stream away from the sun like every other comet ever observed. It points toward the sun. It's called an antitail, and while the term exists in astronomy, what we're seeing here isn't the usual case. Antitails have been observed before, but they're rare and they're optical illusions. Here's how they normally work. When Earth passes through the orbital plane of a comet, we see the curved dust tail edge, foreshortened, and it can appear to point slightly toward the sun from our perspective. It's geometry. It's viewing angle. It's not a real reversal of physics, just a trick of alignment, and it lasts for days, maybe a couple of weeks at most, until our viewing angle changes. What 3i Atlas is doing isn't that. The sunward pointing feature has persisted for months. Multiple observatories have tracked it from different positions, and the feature remains. It's not an alignment trick. It's not a perspective illusion. The particles are actually positioned between the comet and the sun, sustained there against every force that should be blowing them away. Think about what that means. The sun is a furnace radiating light and hurling charged particles in all directions. Anything loose near a comet should be pushed away from that radiation source. That's not theoretical. That's measured, confirmed baseline physics. So how do you get particles to stay on the sun-facing side? You'd need some force stronger than solar radiation pressure holding them there. But what force? Gravity? Comets don't have enough mass to gravitationally hold onto dust against the sun's push. Magnetism? Comets aren't magnetic. Electrostatic forces? Possible, but you'd need a very specific charge distribution, and it wouldn't explain the longevity. Avi Loeb, the Harvard astrophysicist who's made a career out of taking astronomical anomalies seriously, published an analysis in late December where he pointed out something critical. Typical cometary dust is submicron scale, tiny enough that solar radiation pressure easily dominates, but spectroscopic analysis of 3i Atlas's sunward feature shows particles closer to several microns in size. That's bigger, heavier, harder to move. But here's the paradox. If the particles are too big for radiation pressure to blow them away quickly, they're also too big to be held in place by the weak gas flow from sublimation. You're stuck in a physics vice. The particles are the wrong size for any normal mechanism. They shouldn't be where they are, and yet there they are, night after night, observation after observation. The antitail has persisted past perihelion, which occurred on October 29, 2025. After perihelion, outgassing decreases as the comet moves away from the sun. Activity drops, jets weaken, tails fade. That's the standard life cycle. But 3i Atlas didn't follow that script. Its sunward feature remained visible, stable, and strong well into December, long after it should have dissipated. Observers at multiple facilities, coordinating through international networks, confirmed the same thing. The anomaly wasn't fading on the expected timescale. There are attempted explanations. Some researchers suggest that the nucleus might be rotating in such a way that a specific active region is continuously pointed toward the Sun, creating a directed jet that feeds the antitail feature. That's plausible if you can explain why only one jet dominates, why it's so stable, and why the particle sizes are wrong. Others propose that there might be some kind of internal reservoir of volatiles releasing impulses, creating a sustained outflow. Again, plausible in principle, but you'd need a very unusual internal structure. What makes this frustrating for scientists is that you can construct a natural explanation if you're willing to stack enough rare conditions together. Unusual composition? Sure. A typical rotation axis? Okay. Single dominant active region? Fine. Particle ejection velocities in a narrow range that defies typical comet models? Getting uncomfortable, but maybe. Sustained activity months past perihelion? Now you're asking for a lot. See, any one of these things can happen. Comets are diverse, but all of them happening in the same object. That's where the discomfort starts. It's like flipping a coin and getting heads 10 times in a row. It's not impossible. It's just unlikely enough that you start wondering if the coin is weighted, and then there's the emotional reality of watching this unfold. Astronomers are trained to assume natural explanations first. That's the foundation of the scientific method. Extraordinary claims require extraordinary evidence, and the burden of proof is heavy. But there's a difference between healthy skepticism and refusing to acknowledge when something doesn't fit. The observations of 3I Atlas have been published in peer-reviewed journals. The data is public. The anomalies are real. Calling it just a weird comet feels increasingly insufficient as the details accumulate. Space.com ran an article in late December describing the antitail observations, citing multiple astronomers who used carefully diplomatic language, unusual, unexpected, not well understood. That's scientific speak for, we don't know what's going on, but we're not ready to say it out loud yet. Another report from NDTV around the same time highlighted the duration of the antitail as the most troubling aspect, because duration rules out most of the easy explanations. Here's what we know for certain. 3I Atlas has a sunward-pointing dust feature that has lasted months, composed of particles that are the wrong size to be there, sustained past the point where it should have faded, confirmed by independent observers across the globe. That's not speculation, that's documented reality. The question isn't whether it's happening. The question is why. But here's the thing, the antitail isn't even the only problem. If that were the only anomaly, you could maybe write it off as a 1 in a million geometric coincidence. But when you add in the rotation data, when you look at how this object is spinning and where its jets are pointing, the picture gets even harder to reconcile with natural behavior. And that's where we need to go next. Because the rotation pattern of 3I Atlas is where things start to feel less like chaos and more like precision. Rotation is usually a comet's messiest feature. These objects are irregular chunks of ice and rock, often loosely bound, sometimes more rubble pile than solid body. When jets fire from different locations, they create uneven thrust like a lopsided rocket. This causes the rotation to speed up, slow down, wobble unpredictably. It's chaotic by nature. Comets tumble, they precess, they're messy spinners. 3I Atlas rotates with a period of about 15.5 hours. That's not unusual in itself. Plenty of comets have similar rotation rates. What's unusual is the behavior of its jet. Instead of multiple jets firing from random locations as the nucleus spins, observers have documented a single dominant jet that exhibits a consistent wobble pattern over a cycle roughly half the rotation period, which suggests a structural relationship between the spin and the jet activity. Let me give you an analogy. Imagine a garden sprinkler that's slightly off balance, so as it rotates, the water stream wobbles in a regular pattern. You can predict where the water will point at any given moment because the wobble is tied to the mechanical rotation of the device. It's not random, it's repeatable. That's what the jet behavior of 3I Atlas looks like. Observers watching over consecutive nights see the same wobble pattern, phase-locked to the rotation period. Multiple observatories documented this behavior in December, tracking the comet over multiple nights and measuring the intensity variations and directional changes of the jet. What they found was remarkable stability. The jet wobbled, yes, but in a way that repeated precisely every rotation cycle. There was no drift, no decay, no chaotic variation. It was remarkably regular, showing consistent periodicity. Now you might think, couldn't this just be a result of the nucleus shape? If the comet is football-shaped or has one large active region, wouldn't that create a stable jet as it rotates? In theory, yes, but you'd need a very specific internal structure. Most comet nuclei are irregular, pockmarked with craters, fractured from thermal stress. Active regions shift over time as ice sublimates and exposes new layers. Jets appear and disappear. The idea of a single jet maintaining mechanical level precision for months is hard to square with the messy, evolving nature of cometary surfaces. And here's where it gets stranger. This pattern persisted through perihelion. Perihelion is when everything goes wild. The heating is maximum. Multiple areas of the nucleus should become active simultaneously. You'd expect the jet activity to become more complex, more chaotic, with several jets competing for dominance. But that's not what happened. The single dominant jet continued its regular wobble, unperturbed by the increased solar flux. After perihelion, as the comet moved outward and activity should have decreased, the jet's stability didn't waver. It kept wobbling on schedule. Observers kept seeing the same pattern. It's as if the mechanism driving the jet wasn't directly dependent on the sun's heating in the way we'd expect. That's strange. That's not how sublimation-driven jets typically behave. There's another detail that bothers researchers: the jet's orientation relative to the sun. For a sublimation-driven jet, you'd expect it to point roughly away from the sun-facing side, because that's where heating is greatest and gas is escaping. But the wobbling jet of 3I Atlas has been observed pointing at angles that don't align neatly with the expected solar heating pattern. It's as if the jet's direction is controlled more by the object's internal structure and rotation than by where the sun is in the sky. Some scientists have suggested that this could be explained by a deeply buried reservoir of volatiles connected to the surface through a subsurface channel. If the channel has a fixed geometry, the jet would always emerge from the same point at the same angle relative to the nucleus, regardless of solar heating patterns. That would create the stability we're seeing. But you'd need to explain why only one such channel exists, why it hasn't collapsed or shifted over time, and why the volatile reservoir hasn't been exhausted yet. It's possible. Nature can produce highly specific conditions under the right circumstances. But with each additional constraint, with each new but you'd have to also assume this rare condition, the explanation starts to feel strained. You're not violating physics, but you're requiring a very lucky combination of factors. Avi Loeb has used the word mechanical when describing the jet behavior, and that word choice is deliberate. He's not claiming it's artificial. He's saying it looks organized in a way that feels engineered, even if it's natural. It's the same instinct you'd have if you found a perfectly round stone on a beach. It could be natural. Water and time can create smooth spheres, but your brain immediately wonders if someone made it, because the precision feels intentional. What makes this even more compelling is that we have precedent for anomalous behavior in interstellar objects. Oumuamua, the first confirmed interstellar visitor, exhibited unexplained acceleration as it left the solar system. Multiple research teams tried to explain it with outgassing, but the models didn't fit. No coma was observed, no jets were visible, yet it accelerated beyond what gravity alone could account for. The scientific community is still debating that one. 3I Atlas is interstellar too. It came from beyond our solar system, carrying with it the chemical and physical signatures of wherever it formed. We don't know what comet formation looks like in other star systems. We don't know if the processes there produce objects with different internal structures, different volatile compositions, different behaviors than our native comets. Maybe interstellar comets just act weird, and we're seeing natural behavior that's foreign to us because we've only studied comets born in our own neighborhood. But that explanation only works if interstellar comets are consistently weird, and we don't have enough data yet. Oumuamua was strange. 3I Atlas is strange. That's a sample size of 2, not enough for patterns, not enough for conclusions, just enough to make you wonder. The wobbling jet, the persistent antitail, the unusual particle sizes. These are pieces of a puzzle that don't fit together cleanly. Each one can be explained individually if you're willing to invoke rare conditions. But taken together, they create a picture that resists easy interpretation. And as we'll see next, the mystery deepens further when you consider what 3I Atlas is wrapped in. A veil of dust so thick that we can't even see the nucleus clearly. And that veil itself has properties that don't match expectations. In late December, Avi Loeb published an article where he described 3I Atlas as being hidden behind a veil of dust. That phrase stuck with me, because it captures something essential about the frustration astronomers are feeling. We can see the comet. We can measure its brightness, track its motion, analyze the light reflecting off its coma. But we can't see the nucleus itself. It's obscured, wrapped in a cloud of particles so dense that direct observation of the surface is impossible. Now, all comets produce dust. That's normal. The sublimating gas carries dust particles with it, creating the coma that surrounds the nucleus. But the amount of dust and the size of the particles matter. For most comets, the dust is fine, submicron scale, and relatively sparse once you account for the volume of space it's distributed across. You can usually image through it with powerful enough telescopes and the right filters. You can resolve the nucleus, map its shape, identify surface features. 3i Atlas isn't allowing that. The dust production rate is abnormally high, and the particles are larger than typical cometary dust. Spectroscopic analysis shows particles in the several micron range, which is bigger than the submicron dust that dominates most cometary comets. These larger particles scatter light differently, they create more opacity, they block the view more effectively. Why does this matter? Because without seeing the nucleus, we can't confirm its shape. We can't measure its rotation axis directly. We can't identify active regions or map the surface geology. We're essentially flying blind, making inferences from the behavior of the dust and gas rather than observing the source itself. It's like trying to understand a factory by watching the smoke coming out of the chimney without ever seeing the machinery inside. Loeb's analysis pointed out that the dust veil has remained consistent over an extended observation period, even as the comet moved past perihelion and outward. Normally, dust production would peak at perihelion and then decline as the comet cools, but the veil around 3i Atlas has maintained its density longer than expected. That suggests either a sustained outgassing rate that defies the usual cooling curve, or a large reservoir of surface material being slowly eroded and ejected. There's also the composition angle. Spectroscopic measurements have shown that 3i Atlas is unusually rich in carbon dioxide relative to water. The ratio shows significantly more CO2 than water, which is inverted from the typical comet composition. Water is usually the dominant volatile because it's abundant in the cold regions where comets form. Carbon dioxide is present but secondary. 3i Atlas flips that script. Why does that matter for the dust veil? Because carbon dioxide sublimates at a lower temperature than water. It becomes active farther from the sun. If the nucleus is CO2-rich, it could remain active longer as it moves outward, sustaining the dust production when a water-dominated comet would be quieting down. That fits the observations, but it also raises the question, why is this object so CO2-dominant? Is it a result of where it formed? Did it come from a colder, more CO2-rich region of a distant star system? Or is something else going on? Here's where speculation starts to creep in, and I want to be clear about the line between data and interpretation. The data says, high dust production, large particles, CO2-dominated composition, veil persists past perihelion. Those are facts. The interpretation is where things get murkier. Some researchers suggest this is just a natural result of an unusual formation environment. Others, including Loeb, suggest that the veil might be serving a function, not by design necessarily, but by consequence. If you wanted to obscure something from observation, a dense dust cloud would do the job. If you wanted to regulate internal temperature, a thick coma would act as a heat shield, absorbing solar radiation before it reaches the nucleus. If you wanted to mask the source of thrust from jets, the dust would make it hard to pinpoint active regions. Again, I'm not claiming intentionality here. I'm pointing out that the veil has effects, whether those effects are accidental or not. The frustrating part is that we don't have the technology to see through it clearly right now. Ground-based telescopes are limited by atmospheric distortion and optical resolution. Space telescopes like Hubble or James Webb could potentially resolve more detail, but observing time on those instruments is precious and heavily competed for. And even if we got the time, it's not clear we could penetrate the dust veil enough to see the nucleus directly. We might just get a higher resolution view of the same cloud. There's a hope, though, and it's tied to what happens in March. When 3i Atlas passes close to Jupiter, the planet's immense gravity is going to exert tidal forces on the comet. These forces could stress the nucleus, potentially causing fractures or triggering enhanced outgassing. If the outgassing increases suddenly, it might disrupt the dust veil, clearing it temporarily, or it might thicken it further. We don't know, but there's a chance that the encounter will give us a clearer view of what's underneath. There's also the possibility that the gravitational stress could break the nucleus apart. Comets are fragile. Some are little more than rubble piles held together by weak gravity and frozen ice. If 3i Atlas has structural weaknesses, Jupiter's tides could exploit them. If that happens, we'd see the internal structure exposed. We'd get data on composition, layering, density. It would be catastrophic for the comet, but scientifically invaluable. Of course, that assumes the nucleus is fragile. If it's more robust than typical comets, if it has greater structural integrity, it might survive the encounter intact. And that would tell us something too, because comets that survive close passes by giant planets tend to be denser, more cohesive, less like rubble, and more like solid ice. That would be unusual for an object behaving like a comet in other ways. The dust veil is a problem for observation, but it's also a data point in itself. The fact that it's so dense, so persistent, so rich in large particles, those details constrain what 3i Atlas could be. They narrow the possibilities even as they obscure the direct view. It's a frustrating paradox. The thing that hides the truth also reveals clues about it. And here's the final twist. We're not entirely dependent on ground-based telescopes anymore. NASA has a spacecraft, the Europa Clipper, that happened to be in the right place at the right time to get a view of 3i Atlas that no telescope on Earth could match. And what it saw adds another layer to this mystery, because the spacecraft observed the comet from an angle, and with instruments that revealed things we couldn't see from here. That data was released in late December, and it complicates the picture even further. So let's talk about what NASA's spacecraft saw when it looked at this thing from a viewpoint we couldn't access. Europa Clipper launched in late 2024 with a singular mission: to study Jupiter's moon Europa, searching for conditions that might support life beneath its frozen crust. The spacecraft is on a long journey to Jupiter, scheduled to arrive and begin its science mission in a couple of years. In November 2025, as it cruised through the inner solar system on its way out, the mission team realized they had an unexpected opportunity. 3i Atlas was passing through a region of space that Europa Clipper could observe from a unique vantage point. Earth-based telescopes observe comets from our planet's position, which means we always see them from roughly the same geometric angle relative to the Sun. We see the sunlit side, the side where sublimation is most active. But Europa Clipper at the time of its observation was positioned differently. It could see 3i Atlas from an angle that was partially blocked from direct sunlight, a perspective that Earth's telescopes couldn't match. The mission team pointed the spacecraft's ultraviolet spectrograph at the comet and collected data. The observations happened in November, but the data took weeks to download, process and analyze. NASA released preliminary findings in mid-December, timed to coincide with the American Geophysical Union's conference. The ultraviolet spectrograph, designed to analyze the thin atmospheres of moons, turned out to be perfect for studying the gas emissions of a comet. And what it detected was unexpected. The spacecraft measured strong signatures of oxygen and hydrogen in the coma, which makes sense because those are the components of water vapor. Water molecules break apart under ultraviolet light from the sun, releasing hydrogen and oxygen atoms that glow in ultraviolet wavelengths. That's standard comet science. But the intensity of the emission was higher than models predicted for the distance and solar heating the comet was experiencing at the time. In other words, 3i Atlas was outgassing more vigorously than expected, even from the shadowed side that wasn't receiving direct sunlight. That's odd because sublimation is driven by heating, and the shadowed side should be cooler, less active. You'd expect weaker emissions from that region. But Europa Clipper's data showed robust activity even in areas where heating should be minimal. There are ways to explain this. Internal heat could be playing a role. If the nucleus has pockets of warmer material, heat could conduct through the interior and drive sublimation from regions not directly exposed to the sun. Alternatively, the rotation could be bringing recently heated areas into shadow, and the thermal inertia might sustain outgassing for a period after the surface cools. Both are plausible. But here's the detail that caught attention. The outgassing was sustained over the entire observation window, which lasted hours. Thermal inertia can explain brief continued activity after sunset on a comet's surface, but hours of sustained outgassing from a shadowed region suggests either a very unusual thermal profile or a subsurface source feeding gas to the surface, independently of immediate solar heating. Again, not impossible, just uncommon. The Europa Clipper data also provided measurements of the gas velocity and density, which help constrain models of the nucleus's activity. The velocities were consistent with sublimation-driven expansion, nothing anomalous there. But the density measurements suggested that the gas production rate from the shadowed side was a significant fraction of what you'd expect from the sunlit side. That's surprising. For most comets, the shadowed hemisphere contributes minimally to overall gas production. NASA's team was cautious in their public statements, as they should be. They described the observations as providing new insights into interstellar comet behavior, and noted that further analysis is ongoing. That's standard scientific language. But in conversations at the conference, astronomers were more candid. Several expressed surprise at the symmetry of the outgassing. One researcher described it as almost like the nucleus doesn't care which side is facing the sun, which is a carefully neutral way of saying the activity pattern doesn't fit the standard solar heating model neatly. There's another aspect to this that's worth considering. Europa Clipper's observations were brief. The spacecraft was flying past, not orbiting the comet. It got a snapshot, not a long-term monitoring campaign. That snapshot is valuable, but it's limited. We don't know if the high outgassing from the shadowed side was constant or variable. We don't know if it's a permanent feature of this comet or something transient tied to a specific rotation phase or internal event. What we do know is that the spacecraft provided data Earth couldn't. That's the power of in-space observations. Different angles, different instruments, different perspectives, and in this case the perspective revealed activity in a place where we weren't expecting much activity. It adds to the pile of anomalies, the stack of this is unusual but maybe explainable observations that define 3i Atlas. It's also worth noting that this was unplanned science. Europa Clipper isn't a Comet mission. It's not optimized for this kind of observation. The fact that it captured useful data at all is a testament to the flexibility of modern spacecraft design and the quick thinking of mission teams who recognized an opportunity. But it also means the data is secondary, a bonus rather than a primary objective. We got lucky, and what we got has raised more questions than it answered. The real question now is whether we'll get more data like this. Europa Clipper will continue its journey to Jupiter, and it won't be in position to observe 3i Atlas again before the comet's close approach to the planet. Ground-based telescopes will be our primary data source for the March encounter, but other spacecraft like the Juno mission already orbiting Jupiter might have opportunities to observe the comet as it passes. Juno's instruments are designed to study Jupiter's atmosphere and magnetosphere, but they could be repurposed for comet observation if the mission team decides it's worth the effort. And it might be worth the effort, because what happens in March could be the key to understanding everything we've observed so far. The close pass by Jupiter is going to subject 3i Atlas to forces that could change it, reveal it, or destroy it. This is the moment the astronomical community has been waiting for, the event that might finally answer the question, what are we really looking at? March 16th, 2026. That's the date. Mark it if you haven't already, because that's when 3i Atlas will reach its closest approach to Jupiter, passing within a distance that puts it inside the planet's Hill sphere. The Hill sphere is the region around a planet where its gravity dominates over the Sun's gravity. Inside that boundary, objects respond more strongly to the planet than to the Sun. For Jupiter, with its immense mass, that sphere extends millions of kilometers. 3i Atlas will be threading through it. The closest approach distance is about 53 million kilometers. That sounds far, and by human standards it is. You could fit several Earths end-tuned in that gap. But by cosmic standards, especially when you're talking about a planet as massive as Jupiter, that's close. Jupiter's gravity reaches out. It pulls, it tugs, it exerts tidal forces on anything passing nearby. Tidal forces are what happen when gravity varies across the size of an object. The side of 3i Atlas closer to Jupiter will feel slightly stronger gravity than the far side. That difference creates stress. For a small, fragile object like a comet, that stress can be significant. We've seen comets break apart during close passes by the Sun due to tidal stress. Jupiter isn't as massive as the Sun, but at close range its tidal forces are nothing to dismiss. So what could happen? There are several possibilities, and which one unfolds depends on factors we don't fully know yet. The comet's internal structure, its tensile strength, how much stress it can tolerate before fracturing. If the nucleus is a loosely bound rubble pile, the tidal forces could pull it apart, scattering fragments along its orbital path. We'd see the single object split into multiple pieces, each with its own coma and tail. That's been observed before with other comets, and it's always a spectacular event for astronomers because it exposes the internal structure. If the nucleus is more robust, cohesive, held together by something stronger than weak gravity and frozen ice, it might survive intact. But even surviving intact doesn't mean unchanged. The stress could cause surface fractures, triggering new jets from previously inactive regions. It could destabilize the rotation, altering the wobble pattern we've been tracking. It could compress internal cavities, forcing buried volatiles to the surface and increasing outgassing rates. And here's the part that has everyone's attention. The encounter could disrupt the dust veil. If tidal stress fractures the surface and releases a burst of gas and debris, the veil might thicken temporarily, obscuring the nucleus even more. But if the outgassing is violent enough, it could blow the dust away, clearing the view. For the first time since we started observing this object, we might see the nucleus directly. We might map its shape, measure its size, identify active regions. That would be transformative for our understanding. There's also the question of trajectory changes. Jupiter's gravity will definitely alter 3i Atlas's path. The question is how much. A small deflection would keep it on an outbound trajectory, sending it back toward interstellar space on a slightly different course. A larger deflection could bend its path significantly, potentially sending it deeper into the outer solar system, or even changing its velocity enough to affect when and how it eventually leaves our neighbourhood. And then there's the more exotic possibility, the one that Avi Loeb has hinted at in his writings. If 3I Atlas was something other than a passive chunk of ice, if it had any kind of internal activity or propulsion mechanism, the Jupiter encounter might trigger observable changes. A trajectory adjustment that doesn't match gravitational models, a sudden change in outgassing that isn't explained by tidal stress, a maneuver. I'm not saying that's what will happen, I'm saying that's what some researchers will be watching for, because this is the test. This is the moment where natural versus non-natural behaviour becomes distinguishable. A natural comet will respond to Jupiter's gravity in predictable ways. Its path will bend according to Newtonian mechanics. Any outgassing changes will correlate with tidal heating and surface fracturing. The physics will match the models, but if something doesn't match, if there's a deviation that can't be explained by known forces, that's when the conversation shifts. The scientific community is preparing for this. Observatories around the world are coordinating observation campaigns. Multiple telescopes will be tracking 3I Atlas continuously through the encounter window, capturing data on its brightness, position, spectral signature, and any changes in its coma or jets. The Juno spacecraft, currently orbiting Jupiter, has been tentatively scheduled to observe the comet if its trajectory allows. Juno's infrared instruments could potentially detect thermal signatures from the nucleus that ground-based telescopes can't resolve. The Europa Clipper spacecraft won't be in position to observe the encounter directly, as it will still be en route to Jupiter, but mission planners are exploring whether any of its instruments could contribute data from a distance. Every data point matters. Every observation adds to the picture. This is a coordinated scientific effort on a scale we don't see often outside of major missions. There's also a historical parallel worth mentioning here. Oumuamua, the first confirmed interstellar object, passed through our solar system in 2017 and exhibited unexplained acceleration as it departed. The scientific debate over that acceleration has raged for years. Some researchers attribute it to outgassing, even though no coma was detected. Others have proposed more exotic explanations. The debate remains unresolved because we didn't have enough data. We weren't ready. We didn't know interstellar objects could visit us, so we weren't watching as closely as we should have been. With 3I Atlas, we're ready. We've been tracking it for over a year. We have baseline data on its behaviour, its composition, its rotation. We know what it looks like now, so any changes during the Jupiter encounter will be measurable against that baseline. This is the advantage of preparation. This is why the March encounter matters so much. It's not just about what happens in that moment. It's about having the context to understand what it means. Let me be clear about expectations, though. The most likely outcome is that 3I Atlas behaves like a comet, responds to Jupiter's gravity according to known physics, and maybe breaks apart or maybe survives depending on its structural integrity. That's the baseline prediction. That's what decades of cometary science would suggest. And if that's what happens, we'll learn a lot about interstellar comets and their properties. That's valuable science. But there's a possibility, small but non-zero, that something unexpected happens. A deviation, an anomaly layered on top of the anomalies we've already observed. And if that happens, if the data from March shows something that doesn't fit natural explanations cleanly, the conversation will change. Not overnight. Science doesn't work that way. But gradually, as the data is analysed and debated and picked apart, the boundaries of what we consider possible will shift. That's why this matters. Not because we expect aliens. Not because we're chasing sensational headlines, but because anomalies are how science advances. They're the cracks in our understanding where new knowledge seeps in. Every major breakthrough in astronomy has started with an observation that didn't make sense. Uranus's orbital irregularities led to the discovery of Neptune. Mercury's orbital precession led to general relativity. Anomalies matter, and 3I Atlas is an anomaly. A documented, peer-reviewed, multi-observatory confirmed anomaly. The Jupiter encounter in March is our best chance to understand why. It's the moment where forces beyond our control will test this object in ways we can't replicate. Nature is running the experiment. We're just watching, but we're watching closely, with instruments ready, data pipelines active, and minds open to whatever the data reveals. And that brings us to the uncomfortable question. What are the competing explanations for all of this? Because we've laid out the anomalies, the observations, the data points that don't fit easily. But we haven't fully addressed what scientists are saying about it. What are the camps? What are the interpretations? And how much weight should we give to each? That's what we need to tackle next, because understanding this mystery means understanding the debate around it. Let's organise the interpretations because there's a spectrum of perspectives on what 3i Atlas actually is, and they range from conservative natural explanations to more speculative territory. I'm going to present them fairly because cherry-picking only the exotic interpretations would be dishonest, and dismissing them entirely would be intellectually lazy. The truth is probably somewhere in this spectrum, and part of critical thinking is holding multiple possibilities simultaneously until the data forces you to choose. Interpretation 1. Natural comet with unusual composition and structure. This is the mainstream position, held by the majority of astronomers currently analysing 3i Atlas. The argument goes like this. Comets are diverse. We've observed thousands of them, and while most follow predictable patterns, outliers exist. 3i Atlas is an outlier. Its CO2 dominance explains the extended activity past perihelion, because CO2 sublimates at lower temperatures than water. Its single dominant jet could result from an unusual internal cavity structure, where most volatiles are channeled to one exit point. The antitail could be explained by a specific combination of particle sizes, rotation axis alignment, and ejection velocities that create a semi-stable sunward feature for longer than usual. This explanation requires stacking several rare conditions, but none of those conditions violate known physics. It's like rolling a natural 20 on a die. Unlikely, but not impossible. Comets formed in other star systems might have different compositions than ours. Maybe CO2-rich comets are common wherever 3i Atlas formed. Maybe its formation environment produced objects with denser, more structured interiors. We don't know enough about cometary diversity across the galaxy to rule this out. Proponents of this view emphasize that extraordinary claims require extraordinary evidence, and so far, nothing 3i Atlas has done definitively breaks the laws of physics. It's weird, yes. Difficult to explain, yes. But difficulty isn't impossibility. Science has a history of initially puzzling observations that eventually yield to natural explanations once we understand the underlying mechanisms better. Interpretation 2. Unknown natural process. This is a more cautious version of the first interpretation. Researchers in this camp acknowledge that current models of comet behaviour don't fully explain 3i Atlas, but they argue that this indicates gaps in our understanding, not evidence of non-natural origins. Maybe there's a sublimation process we haven't characterized yet. Maybe particle dynamics in CO2-rich Comet behave differently than we think. Maybe interstellar comets, having formed under different conditions, operate by slightly different rules. This perspective is fundamentally humble. It says, we don't know everything about comets. We've studied the ones in our solar system extensively, but they're a biased sample. They formed here, under our sun's specific conditions. Interstellar comets bring us data from other environments, and that data might teach us things we didn't know were possible. The anomalies aren't violations of nature, they're invitations to expand our models. This is a scientifically healthy position. It avoids premature conclusions while remaining open to revising established theories. The downside is that it can become a catch-all explanation. Anything unusual gets filed under, we'll understand it eventually. That's not satisfying, but it's often correct. Interpretation 3. Speculative exotic explanations. Now we enter the territory that makes most scientists uncomfortable, but which Avi Loeb has staked his reputation on exploring. The argument here is that when you accumulate enough anomalies, when you stack enough unlikely conditions, when the natural explanations start requiring more and more special pleading, you have to at least consider the possibility that the object isn't entirely natural. Loeb has documented 13 specific features he considers anomalous in his published analyses, though mainstream astronomers debate whether these truly defy conventional explanations. 13 points where the observations don't fit standard comet models cleanly. Individually, each can be explained with some effort. Collectively, they form a pattern that he argues deserves serious investigation without dismissing exotic possibilities out of hand. What would an exotic explanation look like? Loeb has suggested cautiously that some interstellar objects might be probes or debris from technological civilizations. Not necessarily functional spacecraft, but perhaps defunct equipment, discarded components, or artifacts from long-dead cultures drifting through the galaxy. The odds of encountering such an object are low, but not zero. And if you did encounter one, it might exhibit behaviors that seem comet-like because it's shedding material, but with details that don't quite fit because the material isn't being shed by natural sublimation. The dust veil, for instance, could be debris from surface erosion. The jets could be venting from damaged systems. The mechanical precision of the rotation wobble could be a remnant of internal structure. This isn't claiming active intent. It's asking whether what we're seeing might be the slow decay of something that was once technological, now degraded by eons of exposure to interstellar radiation and micrometeorite impacts. This explanation is speculative. It's not supported by definitive evidence. But Loeb's point is that dismissing it without investigation is unscientific. If there's even a small chance that some interstellar objects are technological in origin, we should be looking for signatures that would distinguish them from natural objects. And if we find those signatures, we should take them seriously rather than reflexively explaining them away. The scientific community's response to this has been mixed. Some researchers respect Loeb's willingness to ask uncomfortable questions. Others criticize him for giving too much credibility to hypotheses that lack strong supporting data. The debate is ongoing, and it's heated at times, because it touches on fundamental questions about how we do science and what level of evidence is required before we entertain unconventional possibilities. The internet speculation. I need to address this because it's out there, and pretending it doesn't exist would be naive. Online communities have latched onto 3i Atlas, and some of the speculation has gone far beyond what the data supports. Claims that it's a functional alien probe, claims that it's maneuvering deliberately, claims that governments are monitoring it secretly. These are unverified, unsupported by peer-reviewed evidence, and mostly driven by the human tendency to see agency in ambiguous data. I'm not including those claims in the serious interpretations because they aren't serious. They're narrative-building, pattern-seeking, the kind of thinking that makes for entertaining fiction but poor science. The legitimate debate is between the three interpretations I outlined above: unusual natural comet, unknown natural process, or speculative exotic origin. All three deserve consideration. Wild internet speculation does not. Where does the data point? Here's my honest assessment. The data currently favours a natural explanation, but with significant caveats. Natural explanations can account for the observations if you're willing to accept that 3i Atlas is a statistical outlier, a rare combination of conditions that produces unusual behaviour. That's not an unreasonable position. The universe is big. Rare things happen. But the caveats matter. The antitail's duration is longer than comfortable. The particle sizes are wrong. The rotation wobble is more stable than expected. The dust veil is denser and more persistent than models predict. The CO2 dominance is extreme. The Europa Clipper data shows symmetric outgassing that doesn't fit solar heating neatly. Each of these is explainable individually, but collectively they strain the natural explanation. Does that mean it's not natural? No. It means we don't understand it yet. And the March encounter with Jupiter might give us the data we need to tip the scales toward one interpretation or another. If the comet behaves exactly as gravitational models predict, if the dust veil clears and we see a normal icy nucleus, if the trajectory changes match calculations, then the natural explanation wins decisively. If something doesn't match, if there's a deviation that can't be reconciled with known physics, then the conversation shifts. And that's where we are, waiting for March, watching the data, holding multiple possibilities in mind, and trying to resist the urge to reach conclusions before the evidence forces us to. So here we are, months of observations behind us, anomalies stacking up, interpretations competing, and a date on the calendar that might change everything. March 16th, 2026. In March 2026, approximately 3 months away. That's when 3i Atlas will pass through Jupiter's gravitational sphere, and that's when we'll get answers. Not all the answers, maybe, possibly not even most of them, but more than we have now. And in science, progress is incremental. Each data point narrows the possibilities. Each observation constrains the models. What should you watch for as that date approaches? What are the indicators that will tell us whether this is a natural comet behaving strangely or something that resists natural explanations? Let me outline the key observables, because understanding what scientists are looking for will help you interpret the news when it starts flowing in. First, trajectory changes. We have precise measurements of 3i Atlas's current path. We have models predicting how Jupiter's gravity should alter that path, based on the comet's mass and approach geometry. When it emerges from the encounter, its trajectory will have changed. The question is whether that change matches predictions. If it does, down to the margins of error, that's strong evidence of purely gravitational interaction. If there's a deviation, something that can't be explained by Jupiter's pull alone, that's when things get interesting. Unexplained trajectory changes were what made Oumuamua so controversial. A repeat of that scenario with 3i Atlas would reignite the debate with new urgency. Second, dust behaviour. The veil that has obscured the nucleus for months could change dramatically during the encounter. Tidal stress might trigger enhanced outgassing, thickening the veil, or it might fracture the surface, releasing gas bursts that blow the dust away temporarily. Watch for reports about changes in the coma's density, brightness, or structure. Watch for images showing the nucleus becoming visible for the first time. If we get a clear view of the nucleus, its shape and surface features will tell us a lot about its internal structure and composition. Third, jet activity. The single dominant jet that has wobbled with mechanical precision might change. Tidal stress could activate new regions of the surface, creating additional jets. The existing jet might intensify, weaken, or shift direction. Watch for reports of changes in the jet's behavior, especially changes that don't correlate obviously with the expected heating and stress patterns. Stability continuing through the encounter would be surprising. Dramatic changes that fit tidal models would confirm natural behavior. Changes that don't fit those models would be anomalies worth investigating. Fourth, spectroscopic data. As 3i Atlas approaches Jupiter, multiple observatories will be collecting spectra, analysing the composition of the gas and dust being released. Watch for reports about unexpected chemical signatures, changes in the CO2 to water ratio, or detection of elements that aren't typical in cometary Comet. Spectroscopy is one of our most powerful tools for understanding what something is made of, and any surprises in the composition data will be significant. Fifth, and this is more speculative, watch for timing anomalies. If the comet's closest approach doesn't happen exactly when models predict, if there's a delay or advance that can't be explained by gravitational calculations, that's a red flag. It would suggest some kind of non-gravitational force acting on the object. Outgassing can create small thrust effects, and that's well documented in comets, but if the timing deviation is larger than outgassing can explain, or if it doesn't correlate with observed jet activity, that would be difficult to reconcile with natural behavior. The data will flow in over several days surrounding March 16th. It won't be a single moment of revelation. It will be a gradual accumulation of observations, measurements, images, and spectra. Scientists will analyze it carefully, compare it to models, debate the interpretations. It might take weeks or even months after the encounter before consensus starts to form about what the data means, and there's a real possibility that the data will be ambiguous. That's how science often works. The encounter might answer some questions while raising new ones. We might get a clearer view of the nucleus, but find that its structure is unlike anything we've seen before, requiring new models to explain. We might measure a trajectory change that's mostly but not entirely consistent with gravitational models, leaving room for debate about whether the residual is real or measurement error. That ambiguity can be frustrating if you're looking for definitive answers, but it's also the nature of exploring the unknown. We're studying an object that came from outside our solar system, from a formation environment we've never directly observed, exhibiting behaviors that challenge our models. Perfect clarity would be surprising. What we should expect is progress, a narrowing of possibilities, a better understanding, even if that understanding includes acknowledging the limits of what we currently know. I want to emphasize something important as we approach this moment. Whatever 3i Atlas turns out to be, the investigation itself is valuable. The process of gathering data, testing hypotheses, debating interpretations, refining models. That's how science advances. Anomalies are gifts. They force us to think harder, look closer, question assumptions. Whether 3i Atlas ends up being an extremely unusual natural comet, or something that rewrites our understanding of what's possible, the scrutiny it's receiving is pushing the boundaries of planetary science and observational astronomy. The March encounter is going to be covered extensively by the astronomical community and the science media. I'll be following it closely, and I'll be here to break down what's happening, what the data means, and what implications it has for our understanding of interstellar objects. This is a story that's still unfolding. We're living through it in real time. That's rare in astronomy, where most of what we study happened millions or billions of years ago. This is now. This is happening. And you're part of the community watching it unfold, so stay tuned. Subscribe if you haven't already, because I'll be covering the Jupiter encounter as the data comes in, and you don't want to miss what might be one of the most significant astronomical events of the decade. Hit the notification bell so you're alerted when I post updates. And here's what I want from you right now. Drop a comment telling me what you think 3i Atlas really is. Are we watching a comet with unusual composition and structure? Are we seeing a natural process we don't understand yet? Or is there a possibility, however small, that this object has an origin we haven't seriously considered? I want to hear your thoughts. I want to know what the data suggests to you, because this isn't just my investigation. It's ours. We're all observers. We're all participants in this moment of discovery. The universe is showing us something strange. It's up to us to figure out what it means, and in less than 3 months, we'll have the best data we've ever had to work with. March 2026 is coming, Jupiter is waiting, and 3i Atlas is heading straight for it, carrying with it the answers we've been searching for. Whatever those answers turn out to be, they'll be real, they'll be based on evidence, and they'll change how we think about what's possible out there in the vast dark between the stars. This story isn't over, it's just beginning, and I'll be here to tell you what happens next.